Right now, while you're watching this, there's a very good chance that a piece of another solar system is somewhere inside our own, and nobody on Earth knows it's there. Not a probe, not anything built by anyone, just an ordinary chunk of rock and ice, ejected from a planetary system light years away, drifting silently through our sun's neighborhood completely undetected. That's not speculation for dramatic effect. It's the actual sober conclusion of astronomers who have spent years doing the math on how many interstellar objects are statistically passing through our solar system versus how many we've actually managed to catch. We've only ever confirmed 3. But the real number, the one hiding behind those 3 confirmed detections, is almost impossible to comprehend. And once you understand how researchers arrived at it, you start to see our solar system very differently, less like a closed private neighborhood, and more like a busy intersection that we've only just installed our first working traffic camera at. Every figure in this video comes from published, peer-reviewed research, or directly from the astronomers doing this work, not from speculation dressed up to sound alarming. And honestly, the real numbers don't need any embellishment to be worth paying attention to. To understand how astronomers even attempt to calculate a number like this, you have to start with the 3 confirmed cases we actually have, because every estimate for the invisible majority is built directly on top of what those 3 visible ones taught us. The first, One-Eye Ice Oumuamua, was spotted on October 19, 2017 by the Pan-STARRS survey telescope in Hawaii, and it immediately became one of the strangest objects ever observed, an elongated, tumbling body with no visible coma or tail, the gas and dust plume that normally identifies something as a comet, moving on a trajectory so fast and so hyperbolic that it could only have originated from outside our solar system entirely. The second, Two-Eye Borisov, arrived in August 2019 and behaved far more conventionally, a genuine, actively outgassing comet, giving researchers their first real comparison point for what an interstellar object's chemistry and behavior might normally look like. Then, in July 2025, came Three-Eye Atlas, larger and brighter than either of its predecessors, an object researchers are still actively studying today, which recently gave scientists their most detailed chemical read yet of material formed around another star, including the first confirmed detection of methane on any interstellar visitor. 3 objects, detected across a span of 8 years. That sounds rare. It is anything but. Here's where the actual math starts, and it comes down to a concept astronomers call number density, essentially a measurement of how tightly packed these objects are throughout interstellar space. Before Oumuamua was ever found, several research groups had already tried to estimate this number using indirect methods, mostly by calculating just how sensitive our best survey telescopes were, and then working out how large a population of these objects would need to exist for us to have detected precisely 0 of them up to that point. Those pre-discovery estimates, dating as far back as a 1976 study, consistently suggested the population, if it existed at all, had to be relatively sparse. Then, Oumuamua actually showed up, and the entire calculation flipped. Rather than confirming a sparse population, its discovery implied something startling. Researchers led by planetary scientist David Jewett, along with several independent teams working the same numbers from different angles, calculated that for Pan-STARRS to have caught an object like Oumuamua on the specific patch of sky and time frame that it did, the actual number density of similarly sized interstellar objects, roughly 100 meters across, had to be somewhere in the neighborhood of 1 object per 10 cubic astronomical units of space. An astronomical unit is the average distance between the Earth and the Sun, roughly 150 million kilometers, so that's the number density measured across a volume of space defined using that yardstick cubed. To put it plainly, the math says these objects are common. Startlingly, almost uncomfortably common, given that humanity had gone its entire existence without ever detecting a single one before 2017. Extrapolate that number density out across the volume of the Milky Way galaxy, and the resulting figures stop sounding like astronomy and start sounding almost like a rounding error gone wrong, the kind of number that's easier to write down than to actually picture. One frequently cited calculation places the total number of interstellar objects, roughly Oumuamua's size, drifting throughout our galaxy at somewhere around 200 sextillion, a 2 followed by 23 zeros, implying a combined mass equivalent to roughly 100 billion Earths worth of material, all of it ejected debris from the countless planetary systems that have formed and shed material across the galaxy's entire history. Other researchers, working from slightly different assumptions about how efficiently planetary systems eject material during their formation, and using more recent non-detection limits and refined survey sensitivity data, converge on similarly staggering figures. The Planetary Society, summarizing this research for a general audience, put a version of the number in especially vivid terms, describing an estimated one followed by 27 zeros worth of interstellar objects residing in interstellar space at any given time. A figure so large it's genuinely difficult to hold in your head in any meaningful way, only 3 of which have ever crossed our path closely enough and been bright enough for us to actually notice. It's worth walking through, at least loosely, how researchers actually turn a single detection into a galaxy-wide population estimate, because it's a genuinely elegant piece of reasoning once you see the shape of it. The core idea relies on something astronomers call a gravitational cross-section, essentially a calculation of how large an effective target a survey telescope is capable of hitting. An object passing near the sun gets gravitationally focused, its path bent inward by solar gravity in a way that depends on both its incoming speed and how close it happens to pass. By combining a telescope's actual observed sensitivity, meaning how faint an object it can detect and across how much sky and time it was actively searching, with the physics of that gravitational focusing effect, researchers can calculate the minimum number density of similarly sized objects that would have been required statistically for that telescope to have had a reasonable chance of catching the one object it actually found. Run that calculation using Pan-STARR's known sensitivity and search history, and Oumuamua's single detection becomes a data point robust enough to extrapolate an entire galactic population estimate from, with appropriately large uncertainty bars attached, but a real, mathematically grounded estimate all the same, rather than pure guesswork. That's also precisely why each new detection matters so much for refining the number, beyond the simple fact of finding another interesting object to study. Every additional confirmed interstellar object tightens the uncertainty on that original number density calculation, because you're no longer extrapolating a galaxy-wide population from a single lucky catch. You're cross-checking multiple independent detections, made under different search conditions, against each other. When 2I Borisov turned up just 2 years after Oumuamua, considerably sooner than some of the more conservative post-Oumuamua population estimates would have predicted, it pushed several research teams to revise their number density figures upward. When 3I Atlas arrived in 2025, larger and easier to detect than either of its predecessors, it added yet another independent constraint to the population models. And its unusual age and chemistry, discussed by researchers, including Cornell astronomer Darrell Seligman, who has focused specifically on characterizing 3I Atlas's properties in the context of the broader interstellar object population, have already started reshaping assumptions about not just how many of these objects exist, but what range of ages, sizes, and formation environments they represent. Now, that galaxy-wide number, staggering as it is, isn't actually the most useful way to think about how many of these objects are near us right now, today, inside our own solar system. For that, astronomers narrow the focus considerably, using the same number density calculations to estimate how many interstellar objects should statistically be present within a specific, more local volume of space, typically defined out to the orbit of Jupiter, roughly 5 astronomical units from the Sun. Estimates using this narrower frame, published by planetary science outreach organizations, summarizing the underlying research, suggest that at any given moment, something in the range of 60 interstellar objects are likely passing through the region of our solar system inside Jupiter's orbit, with an additional roughly 8 objects that aren't just passing through, but have actually been captured, gravitationally bound permanently to our Sun, quietly residing here for good, indistinguishable at a glance from any native solar system object, unless someone specifically traces their orbital history back far enough to notice it doesn't match anything that could have formed here. A separate, more formal study led by researchers affiliated with the Initiative for Interstellar Studies took a different, complementary approach entirely, focusing specifically on the rate at which new interstellar objects should be entering the inner solar system each year, rather than how many are present within a fixed volume at any one time. Their analysis, led by physicist Marshall Eubanks, who also serves as Chief Scientist of Space Initiatives Inc. and CEO of Asteroid Initiatives LLC, concluded that roughly 7 interstellar objects enter the inner solar system annually, following predictable, calculable orbits during the time they're here, a rate that implies dozens of these objects have almost certainly swept through the most populated, most heavily observed region of our solar system within just the last decade, the vast majority of them too small, too dim, or moving through a poorly monitored patch of sky at exactly the wrong time to ever register on a single telescope's sensor. Eubanks himself has described the broader significance of even just the first 2 confirmed detections in stark terms, noting that simply proving these objects exist at all effectively created an entire new field of research, almost from nothing, a field that funding bodies are, in his assessment, only now beginning to properly recognize and support, decades after the underlying theoretical case for these objects existing was first laid out on paper by researchers with no way to actually confirm it. It's worth pausing on why, given numbers like these, we've only actually caught 3, because the gap between the predicted population and the confirmed detections isn't a flaw in the math. It's almost entirely a limitation of what our telescopes have historically been capable of seeing. Interstellar objects are typically small, often no more than a few hundred meters across, extremely faint, and moving fast enough that they only remain bright enough to detect during a relatively narrow window as they pass near the sun, and, if they're active, briefly develop a coma that reflects enough sunlight to register. Before 2017, essentially no survey telescope in operation had both the sensitivity and the sky coverage needed to reliably catch something that faint, that fast, and that rare. Which is exactly why multiple research teams, well before Oumuamua's actual discovery, had already concluded on paper that finding one of these objects would likely require a new generation of far more capable survey instruments, purpose-built for exactly this kind of deep, wide, and fast cadence sky monitoring. That purpose-built instrument now exists, and it's arguably the single most important piece of this entire story going forward. The Vera C. Rubin Observatory, situated in Chile and beginning its flagship 10-year legacy survey of space and time, was specifically designed with sensitivity and sky coverage capabilities that dwarf what any previous survey telescope could manage, repeatedly imaging the entire visible southern sky every few nights, building up an unprecedented, continuously updated map of anything moving against the fixed background of stars. Researchers led by astronomer Dusan Marcheta and Daryl Seligman, a Cornell astronomer who has become one of the leading voices studying interstellar object populations, have already run detailed synthetic simulations, projecting how many interstellar objects Rubin should catch once it's fully operational, testing a range of assumptions about the galactic population's kinematics, reflectivity, and size distribution. Their consistent conclusion across these simulation studies is that Rubin should substantially outperform every survey that came before it, likely detecting new interstellar objects at a meaningfully higher rate than the roughly one every few years pace we've experienced so far, precisely because it's the first instrument actually built with this specific kind of detection in mind, rather than happening to catch these objects as an incidental byproduct of a survey designed for other purposes entirely, like tracking near-Earth asteroids or mapping distant galaxies. Oumuamua itself is worth a slightly longer detour here because the debate it sparked is directly relevant to how seriously the field takes population estimates built on rare, poorly characterized objects. Because Oumuamua showed no detectable coma or tail, the usual telltale sign of a comet releasing gas and dust, and because its brightness varied dramatically as it tumbled, implying an unusually elongated, almost pancake or cigar-shaped structure, unlike any comet or asteroid ever observed in our own solar system, it became the subject of genuine scientific debate, and inevitably, a wave of far more sensational public speculation about artificial origins. The mainstream scientific consensus that eventually formed after years of follow-up analysis favored a natural explanation, most likely a fragment of a more exotic ice, possibly nitrogen ice, similar to what's found on Pluto's surface, that could produce a subtle, undetected outgassing effect on its trajectory without producing a visible coma. That explanation matters here specifically because it's a reminder that even when an interstellar object is genuinely strange, the population statistics that get built from its discovery still hold up, because the number density calculation only depends on the fact that something was detected at a given size and sensitivity threshold, not on fully understanding every detail of what that object actually was. The math survives the mystery, even when the mystery itself takes years to resolve. It's worth spending a moment on what actually makes the Vera Rubin Observatory different from every survey telescope that came before it, because the leap in capability is a large part of why researchers expect the interstellar object detection rate to change so dramatically in the coming years. Rubin's primary instrument is built around an 8.4-meter mirror, feeding the largest digital camera ever constructed for astronomy, capable of imaging a field of view many times larger than the full moon in a single exposure. Rather than pointing at one target for a long exposure, the way many specialized telescopes operate, Rubin is designed to continuously sweep the entire visible sky, revisiting the same patches roughly every few nights, systematically building up a time-lapse record of everything that moves against the fixed background of stars and galaxies. That specific combination, wide field of view, deep sensitivity to faint objects, and rapid, repeated coverage of the whole sky is exactly the profile earlier researchers, including Amaya Moro-Martin and collaborators back in 2009, had already identified years in advance as the minimum capability that would actually be needed to reliably catch interstellar objects, rather than stumbling onto one by pure chance the way Pan-STARRS did with Oumuamua. Rubin isn't a general-purpose telescope that happens to be useful for this. For this specific category of discovery, it's close to the purpose-built instrument the field had been waiting for since researchers first started running these population calculations decades ago. There's a genuinely fascinating secondary implication buried inside all of this math, one that connects interstellar objects to an entirely different, much larger, open question in astrophysics. A team of researchers in Germany, led by physicist Dieter Horns, along with collaborators Nicholas Knopp and Mohammed Adust, recently published an analysis exploring what happens when you take these interstellar object population estimates seriously enough to ask what they'd contribute to the overall mass budget of the galaxy. Their reasoning goes like this. If interstellar objects are genuinely as numerous as the post-Oumuamua number density calculations suggest, and if an object as unexpectedly massive as 3I Atlas, with a nucleus reaching several kilometers in size, is representative of at least part of that population rather than a rare outlier, then the combined mass of all the interstellar objects drifting through the galaxy could represent a meaningful previously uncounted contribution to the galaxy's total baryonic mass, the ordinary matter made of atoms, as opposed to the mysterious non-baryonic dark matter that dominates most models of galactic structure. Their model specifically explores distributing this population across what's called a thick galactic disk, a broader, less tightly confined band of space than the thin disk most visible stars occupy, using rotational velocity data from the Gaia Space Telescope to help constrain how that mass would need to be spread out to match what's actually observed. That doesn't mean interstellar objects explain away dark matter entirely. The amounts involved, while enormous in absolute terms, are still almost certainly a small fraction of what's needed to account for a galaxy's full rotation curve, and the researchers themselves are careful to describe their resulting estimates as carrying substantial uncertainty, largely because the true size and density of objects like 3I Atlas remain difficult to pin down precisely. But it's a striking example of how a population of objects that seemed until 2017 like a purely theoretical curiosity has increasingly worked its way into genuinely significant conversations about the structure and mass content of the entire galaxy, conversations that a decade ago wouldn't have had any reason to mention interstellar comets at all. There's also a wilder, more speculative extension of this same math that's worth mentioning honestly, because it comes from a real published source, even though it sits further out on the edge of mainstream consensus than the core number density work. Harvard astrophysicist Avi Loeb, working with a colleague, published an analysis in early 2026 examining not just the larger kilometer-scale interstellar objects that survey telescopes like Rubin are built to catch, but the vastly more numerous population of much smaller interstellar fragments, meter scale and smaller, that never get spotted by any telescope at all, but instead announce their arrival by burning up as meteors in Earth's own atmosphere. Their analysis, built on records from a catalog of atmospheric bolide or fireball events, estimated that a genuinely enormous number, on the order of tens of millions, of small interstellar objects could be present within the volume of space just inside Earth's own orbit around the Sun at any given moment, essentially arguing that Earth's atmosphere itself functions as an unintentional passive interstellar object detector, occasionally lighting up with the energy of an atomic bomb-scale fireball as one of these tiny interlopers meets its end in our upper atmosphere, entirely unnoticed as anything other than an ordinary meteor. It's a genuinely wild number, and it sits at the more speculative end of current research, resting on a smaller and more uncertain data set than the core population studies built directly on Oumuamua, Borisov, and 3I Atlas. But even set against more conservative estimates, the underlying picture holds. Small interstellar debris is very likely moving through our immediate neighborhood constantly, almost all of it too small and too faint for anything currently watching the sky to ever notice. So what do you actually do with a number like this, practically speaking, beyond simply finding it unsettling in an abstract way? For the scientific community, it's reshaping how future survey missions and even spacecraft design get planned. If interstellar objects really are passing through our solar system on something close to an annual basis, then the long-standing dream of actually sending a spacecraft to intercept and study one up close, rather than watching it fly past from a distance the way we did with Oumuamua, Borisov, and 3I Atlas, starts to look far more achievable than it did a decade ago. Researchers have already begun publishing concrete proposals along these lines, including detailed discussions of what it would take to launch a fast-response interceptor mission capable of reaching a newly discovered interstellar object while it's still approaching, rather than only after it's already passed its closest point and begun heading back out. One such proposal discussed by Avi Loeb in connection with private spaceflight figures interested in funding rapid response missions lays out the core engineering challenge plainly. A spacecraft capable of intercepting a future interstellar object would likely need to be detected at a distance of somewhere between 5 and 10 astronomical units from the Sun, and the response time between detection and launch would need to be extremely fast, since 3I Atlas itself was only spotted at 5 astronomical units, and took nearly half a year to reach its closest approach to Earth's orbital distance, a window that sounds generous until you account for the actual time it takes to build, test, fuel, and launch a spacecraft capable of matching an object moving at tens of kilometers per second. The math on detection rates is precisely what makes proposals like that plausible in the first place. If these objects were as rare as everyone assumed before 2017, planning a dedicated intercept mission around catching one would be a fool's errand, an enormous investment aimed at a target that might not show up again for another generation. If Rubin really does start finding several a year, the entire calculus changes, and a mission architecture that would have been pure science fiction a decade ago starts looking like a realistic, fundable engineering project. One where the hardest part isn't proving these objects exist in sufficient numbers, but building the launch infrastructure fast and flexible enough to actually catch one while it's still worth chasing. Some proposals go further still, suggesting that any intercepting spacecraft carry instruments capable of directly probing the composition of an object's coma before a possible impact, potentially checking for organic molecules or other building blocks relevant to astrobiology, effectively turning a single successful intercept mission into a genuine sample return adjacent opportunity to study material from another star system, with instruments far more capable than anything a ground or space-based telescope could manage from a distance. There's something worth sitting with in all of this beyond the sheer scale of the numbers, and it has to do with how quickly our picture of the universe's own backyard can shift once we finally build an instrument capable of actually looking properly. For the entire span of human history up until 2017, our working assumption, implicit in essentially every model of the solar system taught in every classroom, was that interstellar space was simply empty. A vast, largely featureless gulf separating one star system from the next, with nothing much drifting through it worth worrying about. That assumption wasn't stupid. It was simply the honest reflection of the fact that nobody had ever detected evidence to the contrary. One single confirmed detection, one strange, tumbling, cigar-shaped object caught by one telescope on one particular night in October 2017, was enough to overturn that entire working assumption almost overnight, revealing that the actual population of interstellar wanderers moving through our neighborhood wasn't small or theoretical at all, but potentially numbered in the sextillions galaxy-wide, with dozens quietly present within our own solar system at literally any given moment. We didn't discover that these objects suddenly started showing up. We discovered that they had been there, quietly, invisibly, the entire time, and we simply hadn't yet built the eyes capable of seeing them. It's also worth being honest about how wide the uncertainty bars still are on essentially every number in this story, because that honesty is part of what separates real science communication from manufactured hype. The number density estimate derived from Oumuamua alone carries genuinely large error margins. Researchers themselves describe it as an upper bound rather than a precise figure, and different teams working from slightly different assumptions about size distribution, reflectivity, and how efficiently young planetary systems eject material during their formation arrive at population totals that can differ from each other by an order of magnitude or more. The overall shape of the conclusion, that interstellar objects are far more numerous than pre-2017 assumptions suggested, and that dozens are likely present in our solar system at any given time, holds up robustly across nearly every version of this calculation. But if you see two different sources quoting two different total population figures, that's not one of them being wrong so much as it's the natural consequence of doing rigorous statistics on a phenomenon we've only directly sampled 3 times. Expect these numbers to keep tightening, sometimes moving up and sometimes down, as Rubin's survey data starts rolling in and gives researchers actual detection rates to check their older extrapolations against, rather than working purely from theory and a small handful of lucky catches. That's really the heart of why this story matters, and why it's worth understanding the actual math behind it rather than just the headline-friendly version. This isn't a story about danger, and there's no evidence any of these objects pose a meaningful threat to Earth. It's a story about how much of what surrounds us, even within our own solar system, remains genuinely unmapped, simply because, until very recently, we lacked the tools to look closely enough. With Rubin's survey now underway, that gap is closing faster than at any previous point in astronomical history, and researchers studying this field expect the coming decade to transform interstellar objects from a rare, once-in-a-lifetime curiosity into something closer to a routine. Expected feature of studying our own solar system, one more thing we now know to watch for, simply because we finally built something capable of noticing. Let me know in the comments what you think Rubin will find first, whether it's another strange Oumuamua-style object with no clear coma, another active methane-rich comet like 3I Atlas, or something we haven't even categorized yet, because based on the actual math here, we may not have to wait very long to find out. And if this is the kind of story you want more of, real numbers, real published research, no invented urgency, that's exactly the standard the next one will be held to as well.